Hello everyone, I'm Elena Gramellini and I'm a researcher in particle physics. In particular, I work for the Fermi National Accelerator Laboratory and I am an experimentalist studying neutrinos, which means that in my day-to-day life, I design, construct and analyze data from experiments that are trying to um, unravel the mysteries of the universe in forms of particle, or try to understand in particular a particle called neutrino. So my day-to-day job is a lot of coding, so a lot of Python and C++ writing. And when I'm allowed in the lab, it's a lot of like playing with radioactive sources and high voltages and like really hardcore engineering sometimes. But today I'm going to talk about what, in my extremely biased view, is one of the coolest application of group theory, which is the standard model of particle physics. So the standard model of particle physics is the theory behind what we do in particle physics, what is worth to explore, and building the experiments that I am building. And so it's going to be fun playing a different role for once, because I'm not a theorist, but we're going to talk about theory. And I'm really honored to have this little one-way chat, I guess, with you folks. Um, okay, so what's the standard model? Well, let's take a step back. What's particle physics? Particle physics is the study of the building blocks of our universe. So everything around us, well, even us, like from our bodies to the stars, is made of really, really tiny building blocks, particles. And the way that the microcosm works, so the really like the universe at the smallest scale, is through interaction between particles, between these building blocks. And so the standard model of particle physics, what the standard model of particle physics does is theorizes and predicts the way that particles talk to each other. And since we're talking about particles, this theory is a relativistic quantum mechanical theory or explanation of interactions. This is because particles live in a world that is, of course, very different from ours. Like, we are slow, and here I would say like compact, or you can tell when you are and what speed you're going, but you can't say that for a particle. So um, so particles live in a quantum mechanic world, like the interaction between them and the state of their energies is quantized. And so the description of what they do and how they interact with each other needs to be a quantum description. And most of them are relativistics, meaning that they have a really tiny mass and they go really, really fast. So they don't live in a Galilean world like we do, because they have like a cap velocity, which is the speed of light. So the standard model of particle physics classifies and divides particles in two groups. The fermions, or matter particles, and the bosons, or force carriers. The interaction between two particles, between two fermions, is mediated by the exchange of a boson. So particles from the first category can fill particles of the same category by moving this boson, one of the bosons around. And the metaphor is a little bit like skaters on a frozen lake who are throwing each other a ball, a quantum ball in this case. And, you know, like when a skater throws the ball to the other skater, it's going to recoil. And when the skaters receive it, it's also going to recoil. And so you're going to see a force that, you know, like it's the contrary of attractive, which I can't find the word in English. Repulsive. Yeah, it wasn't a difficult word. A repulsive force. And of course, the metaphor falls apart when you need to model attractive interactions. But in some sense, we can think about the description of the forces, the various forces, as exchanges of different types of balls in between the skaters, and the description of the fermions, of the different types of particles that we have, as different skaters and that can see different balls. The forces that we find in that particles can experience are of three types: electromagnetic, weak, and strong. The electromagnetic has been known for many years, since the 1800s. And of course, when we started to understand that the nuclear structure, we came up with the problem, right? Like the fact that your atom has like a quantized cloud of electrons, and a core that is protons, or this positive core, became a problem because you have charge of the same type that is repulsive by electromagnetic force alone. And so you had to introduce the strong force in order to have something that keeps the nucleus together. And you basically had to introduce the weak force in order to explain a number of phenomena like radioactive decays. So what does this whole have to do with group theory? Well, of course, in order to have a theory that is comprehensive of these three forces and basically accounts for all the particles that we're seeing in nature that are not a small feast, you need both a relativistic and a quantum description of this microcosm of the universe at the smallest scale, made so that you really need kind of a complex, it's not more than complex, I would say, a solid mathematical structure. And that is completely based in group theory and group representation. And so basically, all physics interaction in the microcosm, so electromagnetism, the weak force, and the strong force, are described in the standard model as Lie groups in some particular representation. And the particles that are interacting with a given force, so the fermions that are sensitive to a certain force, a certain carrier, are described by eigenvectors of the Cartan generators of the group. And the eigenvalue of those eigenvectors are physically measurable charges. And so basically, when you're describing a given interaction in the standard model, what you're actually doing is this basically, like the geometry, the geometrical construction of that group defines the physics charge, the thing that you're actually going to measure at the end. And so, for example, like we're talking about eigenvalues and eigenvectors, so the number of charges associated with a certain interaction is equal to the number of dimensions of the representation, because again, like you're looking for eigenvalues. And so, for example, the electromagnetism, the electromagnetic interaction is represented by what is given by the U1 representation. And so it's one dimension, one charge. But when we're describing the strong force, this is a three-dimensional representation of the group that describes it. And so we're going to have three different charges that we call, in probably not the most original way, colors. So red, green, and blue. For the group that describes the weak part of the electroweak force is SU2. So the the force carriers, the particles that are force carriers, are photon gluons and the W and Z bosons. Photons are the electromagnetic carrier, gluons are the strong force carrier, so the balls that where it's exchanged, the particles are exchanged, and W and Z are the carriers for the weak force. And those are described by the generators of the respective Lie group. So again, I think it's, again, like the Lie group are the fundamental descriptors of the standard model, which is the fundamental descriptor of how everything in the universe works at the particle level. Which to me, it just blows my mind. You can have differences in the carriers, of course, that are described about whether or not the force carriers are Cartan generators or non-Cartan generators. And in particular, Cartan generators will interact with other particles by transferring energy and momentum, but will not change the charge from the particles. Instead, non-Cartan generators are force-carrying particles that can interact also by changing the charge. So basically, when you have an interaction, so again, for example, I'm a neutrino, as I was saying, I'm a neutrino physicist, and you can have an interaction where you have a neutrino that exchanges a W boson with one of the quarks of my nucleus and gives out an electron, for example. And you have a charge modification because the neutrino was neutral and you kind of created an electron that has a positive charge or a negative charge if you created an electron or a positron. Anyway, sorry, you started with charge 0 and then you ended up with charge 1. Instead, you could have had your neutrino, which exchanged the Z boson, which is a Cartan generator, and you would have still a neutrino at the end because you didn't change you didn't exchange charge. Okay. Again, like, to me, this is a really cool application, mostly because it basically describes, like, you have the geometry and like you have this geometrical explanation, what I would call a geometrical explanation, an extremely elegant, abstract foundation and very elegant foundation of the standard model, which is really the theory and extremely predictive theory for explaining basically everything in the universe. Well, at least at the tiny, tiny, tiny scale. Okay, thanks for listening. Bye.